Lester, Wishu Engineer. The very first video I uploaded on my YouTube channel was a video documenting the construction and testing of my titanium kukri. I called it Prayer, and I wanted it to be a kind of legacy weapon that I would pass on to my son when I exited stage left, and that he would pass on to his children in turn. I've had a lot of time to play with it, and I love to use it. It is light and nimble, and doesn't suffer from the normal corrosion problems that steel weapons suffer from. As per the testing that I performed in my initial video, it can certainly outperform a similar steel kukri in terms of speed of use. However, titanium is well known for having a particularly high coefficient of friction when compared with other metals. The article entitled Titanium and Titanium Alloys, Wear Behavior and Lubrication, published on AZO Materials, which bills itself as the leading online publication for the materials science community, states the following. The coefficient of friction for titanium in rubbing contact with itself is up to twice the value for steel on steel, and 4 times the value for bronze and other bearing materials. Well, at the risk of stating the obvious, as a blade moves through an object that it is cutting, the sides of the blade make contact with the sides of the object, like so. So as it's cutting through, it's making contact with both sides of the material that it's cutting. And of course, because of that contact, it experiences frictional forces. These frictional forces increase the energy and force required to cut through the object. In addition, if the blade is cutting through a light or unfixed object, such as a small plastic water bottle, high frictional forces between the blade and the object act as a bridge that transfers more of the energy and momentum of the blade moving through it into the object, which can cause the object, and often does cause the object, to move instead of staying in place and being cut. So, in theory, reducing these frictional forces should improve in a blade's cutting performance, should result in better cutting performance for that blade. Despite titanium's high coefficient of friction, in my original video, the titanium kukri did not demonstrate any appreciable decrease in cutting performance when compared with the performance of a similar steel kukri. Could the titanium kukri's cutting performance be improved if the coefficient of friction could be reduced? I thought that this was a valuable question to answer because the outcome may also be relevant to improving the cutting performance of steel weapons and other weapons. I believe that this could be of benefit to the backyard sword cutting enthusiast out there. So how can the coefficient of friction be reduced? Well, quite obviously this could be achieved using lubricants like oil or grease. However, I dislike having oily or greasy blades, and I only put up with this for my steel weapons because they need to be protected against corrosion. In addition, the liquid nature of many standard lubricants may not offer the best reduction in friction that can be achieved for titanium. The article Titanium and Titanium Alloys, Wear Behavior and Lubrication states the following. Standard hydrocarbon lubricants typically reduce the friction coefficient to 0.4 to 0.5 between moving titanium surfaces. It then goes on to state the following. Spray-on film lubricants. A number of proprietary dip or spray-on dry film lubricants based on molybdenum disulfide or PTFE are available, which provide lubricity for severe forming operations such as heading of fasteners, cold forming of springs, thread rolling, and deep drawing. Some of these temporary coatings are very stable and may be left on titanium until all processing is completed. Those based on molybdenum disulfide, which reduce the coefficient to 0.1 to 0.2, which are applied at the start of a manufacturing cycle, may be retained for the service life of components, such as fasteners. Well, I didn't use molybdenum disulfide. I decided that I would test the performance of the titanium kukri before and after treatment using a spray-on dry PTFE lubricant. Wikipedia has the following to say about PTFE. Polytetrafluoroethylene, or PTFE, is a synthetic fluoropolymer of tetrafluoroethylene that has numerous applications. The commonly known brand name of PTFE-based formulas is Teflon. This was what I ended up using. I'm not being sponsored by this product, but this is the product in question. This is something that can be bought easily and cheaply off the shelf from a hardware store such as Bunnings. I decided that I'd use a pair of thick-walled cardboard tubes. These are the remains of the tubes. Of course, I've done the tests already, but these are what the tubes look like. These are the tubes. So I decided to use them as the cutting targets. They were approximately 4 millimeters thick, about 57 millimeters in diameter, and about 980 millimeters long. I had two identical tubes, so I could only perform a relatively small number of tests. In order to standardize the tests as far as possible, I chose to standardize the cutting arc for the kukri to approximately 180 degrees, with no attendant gross body movement in terms of shifting of my feet. I also tried to standardize the amount of energy and force that I put into each of the test cuts. I hung the tubes from the roof of Martel's outdoor covered training area and standardized the type of attachment used. I used cutting movements that were horizontal, or I tried to keep the cutting movements horizontal to the ground, which is of course a suboptimal angle to use for cutting through an object. However, I did this to reduce the chances of accidentally cutting through the tube completely, which would make comparisons very difficult. Despite these precautions, several of the cuts resulted in the tubes being broken from the cut and the associated impact. I could only perform a total of 4 tests on each tube due to the tubes being structurally compromised. I managed a 5th test during the untreated set, but decided to reject that data point. I did so because the tube fractured oddly during that particular test. I must have hit the tube at a structural weak point because the cut wasn't actually notably deeper than the others, but the tube fractured completely. And these are what the tests looked like. I then examined the cuts and measured the length of the cuts using a tape measure along the circumference of the tube. I only measured the parts of the tube that were clearly cut by the blade, so I did not measure the parts of the tube that were fractured. Once I had the cut lengths, I thought I could easily compare those to get the effectiveness of the cutting performance. But that was a bit silly of me, a bit stupid, because the cut length would not scale linearly with the cut depth, because the cut was being performed on a circular cross-section tube. A line bisecting a circle moves through an arc on that circle that's not linearly related to the depth that the line has moved into the circle. So I redid the calculations based on the angle that subtended the cut arc and drew some scale diagrams of the various cuts on my CAD package that I could use to measure the cut depth without resorting to mathematics. And this is what the cut diagrams look like. Note that although the blade of the kukri is notably curved, because of the small relative diameter of the tube, as you can see, I felt that it was safe to simplify the calculation of depth by assuming that the blade was a straight line instead of curved. Finally, taking these cut depths, I was able to put together a pair of bar graphs for comparison. And this is what they looked like. It should be stated that the number of tests performed was really too small to be taken terribly seriously. I only had 2 identical cardboard tubes to test with, so I was limited by my materials. However, the results were very interesting for what they are worth. The average cut depth when the kukri was untreated was 16.37 millimeters, whereas the average cut depth for the Teflon coated kukri was 20.5 millimeters. This represented an improvement in cutting performance of 25% when the kukri was treated with a Teflon coating. If these results represent a trend, which subjectively I believe that they do based on my feeling of the weapon in use, this would represent a very significant improvement in cutting performance. Prior to treating the blade, I performed a few static cutting tests using the kukri on some small water bottles, and these tests were quite disappointing. This is what they looked like. The smaller water bottles were quite tough to cut because their mass is low and their plastic wall thickness is typically greater than the larger water bottles. In addition, the bottles I used were made from a tougher plastic than is usually used in milk jugs, for instance. As a follow-up to these initial disappointing tests, I decided to do some fun cutting tests after the kukri had been treated with PTFE. I got the Wushu scientist to throw some of these small water bottles at me for some fruit ninja cutting action with water bottles instead of fruit. I don't like wasting food in cutting tests unless the fruit is rotten. And this is what the final cutting tests looked like. Let's just
Do the last two?
do the last 2 that I have on the list. I hit one of them, but I didn't quite break it, so I'll just do these after it's 3.
Get a wet shoe.
So, subjectively, the Teflon coated kukri's performance was clearly better. It was like chalk and cheese, actually. So for all of you backyard cutters out there in YouTube land, I challenge you to do some comparative test cuts using your favorite weapons. Compare the cutting performance when untreated and when treated using a spray-on PTFE dry lubricant. If you see marked improvements, post up some videos and let me know. I would be interested. I hope you enjoyed this video, and I'll see you all next time. Cheers.